recording. So, I'm pretty sure we left off exactly. No, I'm just playing. We left off with the fishes, right? We just finished the fishes? The fishes. Plural. You're like, I don't know if that's plural. um, so we're going to do a little bit more of this, a little bit by hand, but mostly GeoGebra stuff, and then I guess we're moving into chapter 7 there. So that's just another formula. We've already seen this formula. I think we already created it once before, but let me just remind you. We have z is x minus the mu over sigma. Again, that's value minus the mean over the standard deviation. And so all they're doing here is just rearranging it. And so this would be, in English, mean plus the z-score times the standard deviation. And that would be your value. So all the same thing. It's just moving formula stuff around. All right. So a veterinarian records the weights of dogs. The weights are normally distributed. Pause. So going forward, they're going to use this word a lot, normally distributed. What that means is that we can use a bell curve. And you know what? I'm going to go ahead and pull one up right now. So in GeoGebra, again, I'm going to go classic, and then probability calculator, and then I got this guy open so we can use it. So if it says normally distributed, I'm like, bell curve. Cool? Okay. With a mean of 52 and a standard deviation 15, so what's going on with these guys here? And I want to use GeoGebra for this, but I think they're just wanting me to plug this stuff in. They're saying what weights are for these z-scores. These are z equals right here. So here's the formula. Let's use it. I really wish I could have used GeoGebra instead, though. All right, so what's my mean again? 52, okay. I'm going to add a z-score. The first one is that negative 2.33. And I'm going to multiply it by 15, awesome. Calculator. Let me pull up Desmos for this, because that's, again, we're just scientific calculator stuff. Scientific calculator. Don't get excited there, James. So 52 minus 2.33 times the 15. And again, plus a negative or just minus either way. I got 17.05. And so that's in pounds. Pounds. And then we just repeat. So 52 plus the 3.10 times 15. Are y'all okay with just, I literally just plugging this into a formula? Yes, Chad. Okay, cool. That's 15. Okay, and here we go. 98.5 pounds and 60.7 pounds. These are dogs, right? Yeah, dogs. Okay, cool. Ta-da! Cool. Straightforward? Good. I mean, it even had the formula right there for us, so that's kind of nice. All right. Oh, yes. Okay, so going forward, we're going to be using GeoGebra to go and find values that are not so easy like that. Perfect example right here. Perfect example. So blah, 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 blah. Let's do this. So average time spent sleeping for medical residents. So apparently they don't sleep much. They have only 6 hours on average with a standard deviation of 1.3. And they're saying how many or how much time is spent sleeping if they're in the top 5% of sleepers. Sleepy doctors. It's like, what do we do? Well, it looks like a bell curve, and I want 5%. In fact, I'm going to use a different color to shade in right here. What would the top 5% look like visually, right? Well, it would look something kind of like this, yeah? Like that little bitty tiny thing on the far end there, top 5%. And so I'm guessing it's going to be around 8 or 9 hours of sleep. Okay, cool so far? So let's go to GeoGebra. And again, we have it all open right here. I have a mean. What's my mean? Yes, 6.1. You can see that from the graph there. Standard deviation, 1.3, type it in. And normally, I would just say, oh, well, if it's right here, and I'm just going to, gosh, Okay, sorry, I pressed the wrong button. There we go. Go away. I would say, oh, it's probably about like 8 hours or so. Now, think about it, like, percentage is not yet 5. Okay, so let me see if it's like 8.5, maybe 8.5. And now we went too far, right? So 8.2, 8.3. That's looking pretty close. 8.35. It's pretty close. But like that would take forever, and they're going to want an exact answer. There it is. Exactly right. Instead of trying to guesstimate right here on this one, just put 5 and we're done. I know, just that easy. Thank you. Good technology skills, right? There we go. So yeah, we're just putting the number in right there, and we get our answer immediately. So 8.3383 hours, and again, that's about what we were thinking, anyways. No! Thank you. Well, that changes everything. Thank you, man. So on your exam, if you do something silly like that, do you think that I would give partial credit? I better. And if I don't, you better come yelling at me. Hey, chat, why didn't you have points? And I'm just like, sorry, you're right. Cool. Okay, cool. Thank you for that. Thank you. Okay, so it says between what two values is the middle 50? I'm going to use a different color. So middle 50. This one's a little different. I'm going to try middle 50 in over here. So middle, right? Middle, this kind of thing. And I'm going to put a 50 in here, right? That's all we did. Wait. I mean, here, like, just as a quick thing, what if I went from 5 to 7, right? So that's around 50. But I want the middle 50. I want it exactly symmetric. Hold on for the folks at home. It's not working. What do I do, right? So let's talk about pictures. If this right here is supposed to be 50%, then what would this side be? 25. And then what about this side over here? Exactly. So what if I did like 25%, basically? You know what I mean? So I'm going to do like 25% on either side. And so instead there, let's do 25 over there. And so then I would have 5.2232 hours. And I guess I have to say between to make it perfect. And then I want to go on the other side. So I'm going to click this guy so it's on the other side. Change it to 25. There we go. 6.9768 hours. So there's your two answers. Is that making sense how I had to kind of draw the picture and say, oh yeah, I see. It's not just 50 in the middle, it's 25 on the ends. So that kind of makes it faster and easier. Any questions on that? Okay, cool. All right. Oh, yes. Bags of raisins. It used to be bags of baby carrots. I love baby carrots. You start eating them and they just get like stuck in your throat and you choke on them. They're great. So, okay, small half story there. I was, back in like 2020, it was like everything was pretty crazy. But I went over to a friend's house and we were having a little bit of carrots and stuff, and like it got stuck in my throat, and I started, and everyone's freaking out. He's like, this dude is starting to cough, and I don't know if this is good. I should not have let him in my house. And I was just like, it's a carrot. It really is. Oh man, it never went back again. Those are the days back in the day. Yeah. So, weights of raisins. Raisins are way safer. We got a mean of this much and a standard deviation that much. Put it in. Like right now, I can start putting this stuff in. I didn't even read the rest of the problem yet. Okay, so we got our bell curve. Everything's ready. So it says bags in the upper 4.5% are too heavy. And again, that lower 5, we're going to do that later. So let's work on the upper 4.5. And so like picture-wise, that would be something that looks like right there, like a little bit on the side over here. So let's chart with 0.045. Look what they're doing. They knew my story now, and they're messing with me. Refresh. Probability. Start over. Shouldn't be telling all this AI all my stories, you know. There we go. So does that look like my picture? And I want to keep drawing the picture every time. I want to make sure, does it look right? Is this what I'm thinking it's going to be? And I got a number. So more than, I guess that's the more than. There we go. That many baby carrots. And then it says also the lower 5% are too small. But now if I put in the 5%, that doesn't make sense, right? That's the upper 5%. So don't I have to do something? What do I have to do? Yeah, switch it, right? Yeah, click a button thingy, right? Switch it over to this thing. And then we can change that to be 5%. And there we go. And so 156.9. 1. There you go. Grams. Awesome. Cool, right? Yay, raisins. Way safer because they're squishy. Good? We'll keep cruising then, okay? Same stuff. Here we go. Oh, that was a whole page. Oh, we're done. So yeah, let's keep cruising. I mean, we got time. I want to keep going here. I'm thinking that next Tuesday, on Tuesday, we can do the chapter application together for this stuff. I don't even know what it's about. I haven't looked, but since we'll probably be done, if not done, then we'll have time anyways. All right, so sampling distributions, et cetera, they're just changing our formula slightly. So mean equals mean, but this is the only thing that's a little tiny different, okay? The bigger zooming out for what we're doing here is that we have a sample size. So go back to the previous problem with our raisins, right? And they gave us a mean, and they gave us a standard deviation, either way, and that was it, done. But now they're going to also give us a sample size. And if they give us a sample size, like a third number, we're going to have to put it in, right? So where do I put it in here? Where do I put n in here? I can't. So what do? Is I use this formula, okay? So this is one of the small times we're actually going to have a formula at all to do this stuff. Whatever that n is, 10, 20, 30, I'm just going to toss it in there with a square root, and that's it. Okie dokie. So for just a quick mini example, let's say it said the mean is 10, and let's say it said a standard deviation of 5. Cool. And then it said blah, 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 sample size of 20. So then whenever I'm going to that mu, what would I put in that box for mean? Just take a guess. 10. Yeah, it doesn't change. Like right here, it basically says the mean is equal to the mean. There's no change here. I'm going to write no change. It's the same as always, okay? But I have to put something new in for the standard deviation box. So what would I put here now? Yes, 5. And then divided by square root of 20. Yep, exactly. And it will accept that. It will accept that. Now what we're going to have to do is type out square root. Unless you want to do it on the side and on a hand calculator, you can do SQRT and then a 20, and it will understand that. It'll understand that. SQRT. I think I didn't do that very well. Let me try one more time here. SQRT. Square root, basically. Cool. So I'm going to do that a lot, like in this section. Every question is going to be like that somehow. And we're just going to add that extra number. Cool? That's all it is. Now, there's a lot more like statistical, like what's really going on, but I just wanted to give you like that's the basics. That's what we're going to be doing like mathy wise, okay? So, it says the population values of this much, 2 slips of paper. Whoa. So find the mean variance standard deviation of this population. I don't think this is part of the homework, honestly. But we can find all this stuff, I guess. So here, I mean, this is going to be so silly. I'm so sorry for you guys. Let's go back to GeoGebra. Classic. And I'm going to go to the spreadsheet. Oh, yes. You remember these good old days, right, guys? All right, cool. Here we go. 1, 3, 5, 7. I'm going to find the average. I'm going to highlight them. One variable analysis. Sigma x. Wow, guys, the average is 4. Did you see that coming? Right? You didn't? Me neither. But wouldn't it make sense? Like it's right in the middle there, isn't it? Yeah. So the average is 4, and we have a standard deviation. And if you notice, we're going to be using this sigma because it said right here population. So that means we're using Greek letters. So that guy right there, that 2.2361, okay? But they had one other piece. Blah, blah, blah. But then you see another number? 2. So I'm pulling 2 out at a time, and that's my sample size. And so then I'm actually going to be doing this standard deviation here. It's not this one. It's the 2.2361 divided by the square root of 2. I'm just following that same formula. Okay, so I can't use this one. I have to use this one now. And again, I don't know what that number is, but that's what we would use in GeoGebra, essentially. Okay, so that's my standard deviation. I don't care about the variance. So it's like we don't use it anyways. Whatever. It says graph a histogram. I don't know what they're talking about here. I don't know. You know what? I can show you a bell curve. Yay! I know you're really excited for this. 4 2.2361 divided by the square root of 2. Oh, look, they even put the little square root on there. Look at that. How fancy of them. And there's your bell curve. Yay! It said histogram, though, Chad. I don't care. It's not on the homework. I mean, if it is, I'll go back and look. List all possible samples. This is sad. Oh, man. Are you ready? List all the possible answers that you can get. Couldn't you get a 1? Is it 1 and a 1? Values are written on slips of paper and put into a box. Okay, yeah, here we go. We can have a 1 and a 1, a 1 and a 3, a 1 and a 5, a 1 and a 7. A 3 and a 1, a 3 and a 3, a 3 and a 5, a 3 and a 7. Isn't this sad? Yeah. Do you think this is on your homework? How would you even put this in your homework? A lot of typing, yeah. We know Newton, okay? They'll probably try to do something like that to us. Construct a probability distribution for the same. I don't even know what they're talking about anymore. But all that's just wasted. We're gonna have to move on. You stop the problem halfway. There's nothing else to do here. It's just being sad when we can actually just do the homework. Like this guy. That's on the homework. This is on the homework. This is on the homework. Okay. But seriously, they're trying to walk you through about why this is so important, but it's not. So here we go. Wow, Chad. I'm being recorded. It's okay. I'm sorry. I'm so sorry. So notice this right here. One tiny thing before we keep going. Sample size greater than or equal to 30. Do you see that? Haven't I talked about that before? It's the magic number 30. Oh, that's so cool. So that's kind of like our cutoff line, but we're going to just keep going right now. You'll see that come up later. Okay, so cell phone bills for residents in a city have a mean of this, a standard deviation that. There it is. Sample size. Blah, 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 blah. Find the mean and standard error. When they mean standard error, they're meaning the new standard deviation, as in like the one that we were going to find. And then, well, there we go. All right. So what's the mean? What would I put in for the mean in GeoGebra? Awesome. So cool. Standard deviation box. I'll make it a little bit bigger. What do I actually put in here? 11. Yep. Divided by square root of 64. There it is. We're done. You don't even need to find what the square root of 64 is. It's 8. But like you don't have to. We're done. That's your standard error. It's the new standard deviation, basically. It's what you're going to be putting in the box. Now it says sketch a graph and all that, but like, here I'm going to sketch a graph. Woo! There you go, right? I mean, what else am I supposed to say? Yay, we did it. Are we okay dividing by square root of n? Okay, I think they're just trying to hit that home. Here we go again. We have a mean. We have standard deviation. Sample size of, 16. Do the same thing again. What's my new mean? What do I put in the box? 3.5, awesome. What's my new standard deviation? What do I put in the box? Yes, 4. Square root of, see, I'm doing both at once. Yeah, it's the square root of 16 or just 4, exactly. Yep, that was it. Awesome. I mean, if you want to find these numbers, that's fine. We might have to do that occasionally. So here we go, 0.2 divided by the square root of 16. And so you could actually just put that value in there. I'm fine with that. I don't know what else to say there. Good? Okay, cool. So hey, Chad, when are we actually going to do some real math? Hopefully now. The mean height of women in a country is this much. A random sample of 55 women. What's the probability that the mean height for the sample is greater than this much here? So this is a value of some kind. And then they have the standard deviation over there. I would say that's the old one. So we're finally actually going to do some real math with this. And I'm going to use GeoGebra for this as well. But let's talk about it for a second, right? Here we go. So we have the mean is at 63.8. Sweet. And it says, what's the probability of 64 or more? Okay, that sounds fine. Well, if I'm looking at a standard deviation about 2.8, that would be this way, right? And I'm going to add 2.8. What, just roughly, if I'm adding about 3, wouldn't that be about 60, 66 about? If I add another 3, 69 or so. Are y'all seeing what I'm seeing there? And watch this funniness. It says greater than 64. 64 right here. Whoop, right there. And it wants greater than that. I don't know about you, but that is really close. Really, 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 really close. Just make a nice rough guess. How much percentage do you think this would be on the bell curve? 49%. That's what I'm thinking too. 49%. But now hold on. That's not exactly what they were asking. And that's the whole thing here. I didn't even take into this 55 at all. So let's understand what they're really wanting out of this kind of situation. They're saying, okay, I have 55 women. What's the probability that the average of that group will be 64 or more? Okay, so think of it like this. If I take one individual, male or female, and I say, hey, let's take you versus the average. They could be all over the place, right? We got 7 foot tall, we got 4 foot tall, all over the place. But now I'm going to take 55 people, and I'm going to find their average. Do you think the average of 55 people is going to be from around 7 foot, 4 foot? I mean, an individual can be that way, but 55 people, we're probably looking at around 5.5 feet. Regardless, you can take any 55 people. I mean, unless it's like 55 people on a basketball team, but that's too many people on a basketball team. So anyways, like I'm saying, like if you're looking at just a very specific group, sure. But I'm just saying 55 random people, we're probably going to get about the same average. And so that's what I'm saying here. We're looking at 63.8. They're guessing around 64. It's really close because that's what we're thinking. I mean, it's like, it's not going to be very far off anyways. So let's do the math. Let's do the real math now, okay? I want to put in my new mean. What would I put in the mean box? 63.8. Got it. What do I put in my standard deviation box? There you go, 2.83, and then divided by SQRT, and I'm going to open the parentheses. It just automatically does that there. Of that, 55, exactly. Okay, so that's my new standard deviation, or standard error is what they call that. So now I want greater than the 64. 64, oh, come on, man. Oh, 64 goes here. My bad. Wrong side. There we go. There we go. And so, like, consider the difference. See you later. A lot different, right? I mean, I know it doesn't seem like a lot different, but let me tell you, that's a lot different. And so that's my answer. We're done. We did all the math. Did we put every number into GeoGebra? Did I put this number in there? Okay, good. Did I put this number in there somewhere? Did I put that number in there somewhere? Did I put that number in there somewhere? So we're good to go. I used all the numbers. There it is. So it's not this. It's technically then 30%, like literally straight up 30%. So I would just pay 0.301. There you go. Cool. But let's go see, were you right about the 49? If I did an individual, I'm going to take out the 55. And I want greater than 64. Why are you stopping? GeoGebra. I like you, but I don't. Hold on. 63.8. 2.83. Here. 64. There we go. Look, that was a lot closer. Look at that. But when we have a group, it's a little different story. Cool? That's what they're trying to get at here. I think that really, just between you and me and the workbook, I wish that this would have been up front. I wish this would have been the math that we could talk about beforehand. I think that all of this stuff is just, well, it's silly. Okay, I don't know what they're doing. But here we go. Let's keep going. So a graph shows the length of time spent driving each day. A lot. I have 100 drivers aged, okay. So they're a little younger. I don't know if they're going to be driving as much as I do. Probability this and that, between this and that much. Okay, so let's kind of like put this all together here. Notice that we're in the 15 to 19 range. See them right there? And so that would be this as my average. Oops, average. Okay, so that's the number that they're wanting to use. Let's put all these numbers in. Let's see if we can do this. Every number needs to go in here somehow. What goes in my mean box? Yep, 25. Okay, what goes in my standard deviation box? Very good, 1.5 divided by square root of the 100. Very good. Yep, so again, that's my sample size. That's my old standard deviation. I put them together, right? And then I have my mean, which I just found right there. Now, this 15 to 19 we don't really need because we already used it for this. But you can see it says between these two numbers here. I'm going to put them in there. Between two numbers. You got it. You got it. There we go. Okay. So here and way over there at 24.7. And I'm just going to do this here, 25.5. And all this here, it made 97.68%. Okay. So what does this mean? Right? That seems like a really huge number here, right? Again, that's not one individual. That's on average. So I take 100 drivers, okay? And I'm saying, is your average somewhere around the 25 range? I mean, isn't that what I'm saying here? Is it somewhere around the 25 range? And they're saying, yeah, it's around the 25 range. Go figure. You know what I mean? And like, how many did we ask originally to find this 25? Probably about 100. Like, it's almost like a duh situation. You know what I mean? That's why it's 97%. It's like, yeah, I mean, that's what we're gonna do. We're gonna find the same number, basically. Cool. We're waiting on one person. I know you're wanting that. He should be showing up soon. Hopefully, maybe. I'll give him another 10 more minutes. 10 more minutes. Is that okay? And then you're gonna steal my computer. I understand. You're good. See ya. So, height of women, and we got a mean of this, standard deviation that. Oh, is it more likely that you'll select one woman that is less than this much, or from a sample of 22 less than that much? It's a pretty interesting question. So I'm going to draw a really quick picture of what we're talking about here. And so I've got the mean is 64.5, and the general standard deviation is just 2.4. So I'm going to go 2.5-ish, 5, 7, 67, 69 point, no, 68.5, no, 9, it's 69.5. Okay, and on this side, if I subtract 2.5, 62, 59.5, just roughly, you know what I mean? Okay, so less than 65. 65 would be, well, well, it's like right here. There's 65. Yay! So what's the probability of less than 65? If you're looking at just one person, just give me a rough number. What do you think? 55%. I love it. 55. It definitely looks about like that. But what about 22 women? Now, so we're going to change some numbers. We're going to look at what it looks like, but here we go. Let's do it together. So I'm guessing for 55 on this first one. The mean, 64.5. Standard deviation, 2.4 divided by square root of what? 22 for 22 women. But notice what the very first question's asking for. It's 1. I can actually just put a 1 down here. It would be fine. Like, what's the square root of 1? And so then I'm dividing by 1. It doesn't really change anything, right? So if you wanted to just have that formulaically, that's fine. We'll just change that number in a minute. And then I'm going to do less than the 65. And look, that picture looks about right. Whoa, pretty close. So yeah, it turned out to be 58.25. Do you see the strength of approximating this stuff like ahead of time? I now know that if I'm going to be way right or way wrong. Is that, yeah. The one, oh, these guys. This is between two numbers, and then this is outside of those two numbers. Yep. Good question. Very good. And it is kind of interactive. You could just like, oh, whoa, I don't know what I just did. Never mind. It's not interactive. Don't do that again. Can I like get back? Refresh. We'll just refresh. I'll never do that again. Thank you. Good question. Good question. Yeah, I thought that would be really fun, but no, that was terrible. So terrible. Okay. 65. All right, cool. So part B, it says now we're looking at 22 women. So n equals 22 now instead of just the 1, right? So I'm going to change my 1, my square root of 1 to square root 22, and then like hit enter, basically. And I got a whole different number, 8358. Okay. Again, what it does is it pushed it back further. It pushed it back further. And the reasoning for that, I'm going to try to do this. This is a very difficult exercise, but I'm going to try here, okay? Let me draw this right on top of one another and show you what's going on. So there's my original. I'm going to say there's my original here. And then I'm going to draw the new one. And it's always tighter It's like a tighter amount. So this right here is always the 64.5, right? And then my 65 is always right here. But now, do you see if you look at just the green curve, it actually is a little bit further away from the mean? I know that sounds kind of weird. But like if you look at the red, it's like only a tiny, like distance wise, it doesn't look any different. But if you're looking at the area there, it actually is a lot more red. So which area is more, right? The green, because it's taller. It's yeah. It's very difficult to draw. Okay, I try, but like it's squishing it so that you get different values. Okay, is it unusual to select a single woman at 65? So they're looking back at this. Is this unusual? No, no, that's fine. We're looking for 5%, 0.05. Okay, so I would say for that one, no. Is it unusual to select 22 women, average of? No. So is this unusual? You're going to say no. Again, you're looking again for 5%. 5%. There we go. I love the lumber cutter problem. It's like one of my favorites. So I'm just looking ahead right quick. Milk containers, got this guy, this guy. Yeah, there's plenty here. I might stop a little early because we've had half the class already walk out, so it's okay. But I'm going to do the lumber cutter problem. I really love this problem. I think it really encapsulates what's going on here. And then after that, we'll just assess. Is that cool? I mean, we are kind of ahead. You're definitely agreeing. Your lumber company has bought a new machine that cuts things automatically, and they're looking for things that cut at 96 inches, so 8 feet, standard deviation of 0.6. So they run 48 boards through it, and they find this mean, and they say, is it broken? And so we're looking to see an average of straight up 96. I didn't get that. I got 96.2. That's only off by like this much, right? Yeah, very tiny. But then again, it's not one board that I ran through. I ran through 48 boards. 48 boards, and that was the average that I got. So something might be a little off. I don't know. So let's go through the math and see if that makes sense. Assuming that it's correct, what's the probability of the mean of this or more? Oh, they're just jumping right into it. So normally the lumber cutter problem does a single board versus a lot of boards. Okay, so I'm going to do one board, and then I'm going to do the 48 boards. I'm going to compare them, okay? So one board, 48 boards. Let's look at the different probabilities. What do I put in for my mean? 96. They want inches for everything here. Standard deviation of? Yep, 0.6 divided by the square root of? Let's start with 1. Yep, starting with 1. And they're saying, what's the probability of this much or more? So that would be my 96.2. So for one board, I got a probability of 3694. So about 36% probability you run this board through there, 36% probability that it's a little bit bigger. And I mean by a little bit, right? That's not too bad. I mean, I guess 30% of them are going to be a tiny bit bigger. Okay, whatever. But what about 48 boards, right? So now I'm going to change it. Square root of the 48 now down here. Whole different ball game, right? I mean, look, my number has drastically changed. One board, no problem. 48 boards, now there's a problem. It's like it's always off. It's not just off one time, it's off 48 times essentially. Hi, sign in now, and James is going to take the computer away. Yes, thank you. Yes, perfect timing. So that's 1%. I'm going to ask, is that unusual? Yeah, unusual. Unusual. Again, we're looking for 5% or less. 5% or less, that's unusual. This is almost nearly very unusual. All right, so it says it appears to be accurate or inaccurate. If 48 boards and I run through and I'm getting a 1% chance that all this is even happening, that's kind of odd. It's just strange. It's very weird that I'm not getting the right answers. So I'm going to say it's inaccurate. Something's wrong here. The mean should be unusual, because if it's true, it wouldn't be happening like this. Again, unusual means less than 5%. I'm just like labeling it here, you know. Assuming that it is true, though, would it be unusual for an individual board? Well, we just did that, actually, didn't we? And that was the 3694. So is that unusual? Is that... No, that's not unusual. That's normal. So I'd say not unusual. That's a typical board. 1, that's fine. 48 of them, no good. So would an individual be fine? I would say yes, it is within the 2 standard deviations of the mean. Yeah, I don't know. That's just basically that unusual stuff again. Not unusual. Cool? Is that making sense? Okay. So again, we're just changing the numbers, and it changes the whole ball game there. So we got milk containers, we got library patrons, yeah, jeans. Now that's a huge table. I don't think we're gonna make it through the whole thing anyways.